Okay, welcome to the final chapter of Module 5. It's got quite a lot of factual stuff, so I'm going to have a quick run through on the facts, stuff that you've done from your research. In this one, I'm just going to put some things in that may not be explained, but by watching the videos, by watching the lessons, that is, you'll pick out the detail. Okay, so I'm going to concentrate on things there. So we're going to just go over the main bodies in space, different parts, the concepts in its biggest picture, and then end up with a little bit on the Hertzsprung-Russell diagram, but very, very briefly. Okay, so just so you can fill your notes in. Okay, so what we'll do to start with is just know our way around the basic idea. So anything in terms of what we're after, anything you need to be able to know your way around is used in the right context. Simple words, just make sure you're using them right. So, any object, any body moving in an elliptical orbit around a star is a planet. It has to have enough mass to actually form its own spherical shape. And what it will also do is, because of that large enough mass, it will attract other things by gravity. So, planet is not just something in orbit around a star. Okay, any body that is moving around a planet is some sort of planetary satellite, okay, of which there are two varieties. And watch the spelling on that. So 1T, 2T, T, a single T at the start and the end, and a double L in the middle. Occasionally catch it out for spelling, and they use that for one of their parts. So, can be man-made, can be natural. Any object that is in orbit around a planet. Other things that are in orbit around stars don't have to be planets. One of the most obvious one is something made of rock, dust, and ice, and they have a very, very different orbit itself, so they're a quite unique body. So comets are just some completely quite small, irregular, the one I showed you the other day looks like dumbbells or a rubber duck. Any system containing stars with planets in orbit around it is a solar system. Now we tend to just use system when you start getting into the field, but we'll call it solar system to just make it clear. Actually, Sol is our sun, so actually this is the name of our solar system, but there we go. Large collection of stars, okay, starting to build up in scale here, so much, much bigger than solar system, is a galaxy. And then the bit that matters most is everything that we know about, whether it exists or not, is the entire universe. So that's not just a collection of objects, it's the whole lot. It's the forces, it's time, it's space in its 4 dimensions, and so on. So it's the whole of knowledge, okay, observed knowledge. So, GCSE, you should have done a bit on this, just summed up nicely, quite nicely in this diagram, here's the colour printouts for you. Stars are formed just by dust being pulled together. It's the mass of it all that pulls it together. It's quite diffuse, so it takes a long time to pull together, but it all comes from that nebula. Okay, so lots of pictures in the PowerPoint and so on. I think it's nice and clear. So nebula is actually what's formed at the end of the whole process. Dust is flying around in space all the time from previous solar systems and stars that have broken down. It's massive recycling, literally massive recycling. Okay, as we start to build that up, again we'll go into details more, but you basically get the gravitational energy, so the gravitational potential energy, converting the forces into thermal energy. Okay, so work is done during collisions to get heat. Now this heat, as it gets more and more collisions, just like a gas, if you get them to collide fast enough, you'll end up forming something that is visible to the naked eye. You can see it actually glowing. However, it is not yet a star. So if you haven't studied this at GCSE, you need a bit more from the videos to say. It's known as a protostar. an almost star. However, it doesn't become a true life star, a star in its main sequence is the phrase we use, until you get nuclear fusion happening. Okay, so that's got to be much, much, much more massive. And what's happening there is the dust, and more usually the gases within it, hydrogen, the most copious amount of copious volumes out there, start to fuse into the next element up, which is helium. It's a chain process, but we'll go into that another time. Okay, star is formed, and in this thing is, as I say, what we call main sequence. And what it is basically stable. It doesn't sit there quietly, but it is basically stable. It's not shrinking, it's not expanding outwards, and that's what's stopping it collapsing inwards any further is the heat producing what's known as radiation pressure. Now it's a bit vague, it's much more vague than the gases idea of pressure, but basically particles are bouncing around, and because of the high density they collide off each other. Okay, now the crucial bit is this is the same for every single process that starts a star, doesn't matter how big it is, and once you run out of fuel then things change. So at this level, to be more precise, again don't use the word fuel, but hydrogen is the fuel there, so once the hydrogen gas runs out it will stop and things will change. You still have heat being produced, you've still got fusion happening, you've still got gravity, the gravitational attraction. However, depending how big or small it is, you get this difference of views, a difference of endings, shall we say, to life of the stars. So, the crucial dividing line, known as the Chandranskhar limit, is that if you are about 1.4 times bigger than our sun, okay, our star, the sun, then what will happen is something else. If you are smaller, you'll end like our star. We're basically going to kind of fizzle out a little bit and swell up into a red giant, and then eventually a white hot dwarf. Okay, so generally all stars have one or two endings. The steps they go through are fairly straightforward, but let's just kind of pick it up. So once the hydrogen has been used up, okay, the nuclear fusion process that we've got going on, okay, I should say some change, nuclear fusion stops. Okay, it's fairly quick once you start running out, but it may still have some hydrogen in, but it's just too far apart to actually collide with each other to form more. What happens is then you've no longer got that pressure pushing outwards, and so we've only got the inward force due to the gravitation. So the net force, if you want to put overall force, resultant force might be a better thing, but the net force inwards leads to it contracting. Now as it does that, the more dense stuff contracts faster, leaving the outer layers behind, and you actually kind of get an expansion effect. So it actually swells up, and the energy inside the star itself actually spreads out. And so what happens is they cool and become less bright. They change their spectral colour, so they become red giants. Now there are different sizes of giants. There's red giants and there's red supergiants. But we'll come back to that. It's just, again, it's kind of a way of classifying things. Okay, now as this is collapsing, the temperature gets higher and higher because you're starting to get inside. So what happens is, once it gets beyond that certain point, this, activation energy, then what happens is we get other effects going on. Okay, so helium fusion then starts happening, and what you get is more massive elements. Okay, as in the next one's up on the periodic table, e.g. carbon and oxygen. Oops. Okay, now again at GCSE you might have got a slightly different story, but actually this does happen, but it's on a very small scale. And what this does is it produces a very tiny but very hot internal core effectively to the star. So the outer bits expand off because we can't get it to keep going. It's just not got enough energy because it's not got enough mass, so therefore not enough gravitational energy to keep the process running. But it's that hot enough for things to start happening. You end up with the white dwarf stage where you've started to create a bit enough, but not enough for nuclear fusion to continue. Okay. I didn't quite leave enough space there. Never mind. Okay, so it really becomes a white dwarf. White hot, very hot indeed, but obviously it's not producing any any more energy. It's not releasing energy, so it's going to cool down over time. Brackets. So what happens after that is effectively summed up on the top of the next page. Okay, so your average star swelling, the inside of that is collapsing at the same point though, so you're starting to get that core building up in heat. Meanwhile we lose the cooler outer things itself. We'll come back to how we know the temperatures of this, because this is all about studying the light. Now this little idea with the white dwarfs, just this extra bit at the end, this is where, and this key term keeps coming up now, it collapses, okay, but it's not enough mass to overcome the repulsion between the electrons. So the electrons do not degenerate. Okay, so electron degeneracy pressure is basically this pressure built up by the repulsion of the electrons. And so because of this, it's the idea, we're basically links in with quantum mechanics. I'm going to link in a bit more here, where Heisenberg's uncertainty principle, Pauli's exclusion principle in quantum. I'll try and write and speak at the same time, it's not good. So where quantum mechanics prevents the the atoms compressing further. So this is not the pressure of the gas, this is pressure within the atoms themselves, the electrons not collapsing. Okay. Now this limit, okay, as I said before, is called the Chandranskhar limit. The largest possible mass to turn into a white dwarf is, let's say, equal to 1.4 times mass of the sun. Okay, obviously our sun, every other sun is called stars. Now you can figure out the rest. If you've gone beyond this, then you've got a slightly different process. If it collapses because it's much more massive, then the process runs on for longer, and you've got a lot more heat and energy being thrown around. So in this one, once the hydrogen stops, so I should say H2, fusion stops, the core collapses, and because of that collapse, and it collapses very rapidly, so let's put that in, rapidly, and heats. So they heat up like it did before, but this one is a very rapid process compared to the fading out of hydrogen in the other one. Okay, you're much more likely to get the fusion carrying on because that mass is being pulled together at a much greater rate because it's so massive. Now because of that, you get a shock which effectively blows the outer layers outwards, and they expand outwards to form, as mentioned before, a very similar process to before, but to form a red supergiant. Again, much more quicker the process than the last one. Okay, now there is a bit of watch out on this. We'll come back to that because it can happen. You know, how do you tell the difference between a giant and a supergiant? A small supergiant looks very much like a red giant, but we'll come back to that when we look at the Hertzsprung-Russell diagram. Okay, as there's so much heat and the energy being released in fusion means that those heavy elements beyond the next ones up in the periodic table can happen. Okay, it's harder to make, so it requires more energy, but basically each time at each stage of collapse, the radon pressure and the electron degeneracy prevents total and utter collapse like it did before. So it's not just collapsing, the fusion element and the heat and the electron degeneracy prevents it happening. But fusion will continue until the most stable ion is created or reached, and that is iron. When we get on to next module, when we look at radioactivity, you'll see the stability charts for different elements. And iron is the peak or the trough, depending how you look at it. So once you reach iron, you can't go any further through the periodic table because it actually takes more energy to form the next layer up in fusion than you do actually get from the fusion process. So what happens is when you get to the iron stage, the core can't take it any further, it collapses. You get a breakdown of this, the atomic structure itself, and electrons collapse in on themselves. They can't support that core, that under pressure. So it undergoes complete and utter gravitational collapse if the mass is greater than the Chandranskhar limit. Chandranskhar, I can never spell this, limit. Okay, or in the exam you can get away with saying greater than 1.4 times the mass of our Sun. So the rapid collapse itself releases huge amount of heat, so thermal energy. More importantly, it sends out huge amounts of electromagnetic energy. You get huge spikes of plasma and other charged particles shooting out through space and so on. And which causes, if it was near to us, it would cause the wiping of cards, your bank cards on Earth. Just that huge electromagnetic pulse coming out. So if the core itself remains together, notice it's an if the core remains together, it doesn't collapse completely, so after the collapse, it doesn't break up, that is. What you'll get is a neutron star. And basically the density of that is the same as the atomic nucleus, so it's a very, very, very dense star indeed. It's collapsed to a very small level. So that's if it remains together. If it doesn't, then what happens is basically if it's really massive, it tends to collapse and come apart much more. So the neutron star itself will collapse. The internucleon forces is overcome as well. So the actual nucleus itself collapses. And so that gets to that happens at around about. So I'll put approximately equal to 3 plus times the solar masses. So if it's more than 3 solar masses, let's just change that actually, make that to approximately greater than 3 or more solar masses, the neutron itself, the neutron star, will collapse instead into a black hole. So forming a massive condensation, a huge mass within a small region, you start getting a rather rather extreme events in terms of gravity and so on because of the density of what's left over. Now, a little bit of interest, a little bit beyond where we're going really. There's a lot of research still going on about this, so we don't really know. But what we've got is the neutron star itself, being small and really dense, causes quite an immense bending of space. What it does have is, as it spins and collapses, it spins very rapidly. What we get is the magnetic field of neutron star is very large, and they rotate rapidly. Generally, we can pick those up as they rotate. They emit radiation, electromagnetic radiation, I should say. And I'll put impulses. Now, it tends to not be pulsing so much, although there are frequencies from it, but as they're rotating, we tend to detect them as pulses. So they're rather like lighthouses sweeping around. If it comes past us, we detect that pulse, we see that beam, and as it spins around, we see the other end, we see the first end, we see the second end. So as it's rotating, if it sweeps over us, then we pick up that pulse. Often called pulsars, strangely enough. Black holes, again, a little bit beyond where we're going. It distorts, it warps, I'll go with distorts, it's a bit more scientific. It distorts the fabric of space-time. So it actually distorts space around it, and it's so great that basically we cannot, our idea of our potential energy wells distort back on themselves, they kind of swell out underneath. It's so great that basically anything, even if it was going fast enough, accelerating down towards that hole, you would actually get pulled in, and it wouldn't be able to come back out again, rather like like it does with normal massive stars that are warping space. So gravitational lensing, this is so great, it won't lens, it will just actually pull in the light. So often said, even light, photons are trapped, okay, are pulled in. They're not pulled in by gravity, but the warping of space-time, which means that they actually get in there. And as I said very clearly in big letters, we don't understand them. The physics is still going on with that, a lot of stuff. So, the last bit, I can't explain this a great deal better. In fact, I can't explain this as well as the graph does. So the video with the lamps, if you watch that, I know it's quite long, but it's a really nice description of what's going on. Effectively, it is a graph of temperature of stars against luminosity. Now, be very careful. We study luminosity, some exam boards and a lot of different universities and so on, what they have is relative luminosity. Okay, so we're going to just be really careful here. When you're looking at this, apparent brightness is effectively what they've got up the side, whereas actually we are looking at actual brightness, actual light given out by it. Okay, so slightly more important in many ways. Also worth noting, the temperature scale is going down. Okay, so this is the low end, this is the high end. Again, I don't know where it came from, but it's always been presented this way. So if we think about this, what this is basically grouping an idea of finding out where something is within its life cycle. All stars follow this life cycle, so actually by looking at the colour of the light and relating it to the temperature, we can find out whereabouts in a star cycle any star is. Effectively, you've got this whole idea where most stars are in their main sequence, okay? And our sun, around about luminosity of 1-ish, slightly lower, so let's say it's, I'm just going to put sun, okay? somewhere in this region. It's an orangish star, so it's around about 6,000-7,000 degrees. 6,000-7,000 Kelvin, not degrees Kelvin, just Kelvin. And say its luminosity is quite low. It's not quite 1. Again, we'll look at definitions when we go into the radiation part. Now, what happens is if you take your original cloud nebula. Okay, so there's different types of nebula, just to kind of go with shape. But if we basically take our cloud of dust and so on, what happens is that's really low temperature. It's more off the scale there, so ... And what happens is as it heats up, we start going sideways. It's luminosity gain, so effectively we start coming into this idea. So protostar stage is coming in here as it heats up. When it gets to the main fusion, then we're somewhere on here. So hinting from this, we have stars of different colours. Why? Because they're all at different temperatures. Why? We can tell from their brightness, but also their colour. And the main reason is that these are much more massive stars up here. These are the smaller stars. So their rate of reaction being pulled in together is much bigger because gravitational field forces are bigger here. So they're reacting faster, so hence they're hotter. Okay, so that's kind of the main difference along here. But most things will then, as they go up, for example, our sun at some point will come upwards into becoming a red giant. And then what happens is the red giants will tend to go through these stages. So it kind of changes temperature, it looks bluer and stuff like that, and then settles into this kind of white dwarf stage. So effectively that's the story of our sun, okay, our star, our middle-aged, like basically along here. Most stars are in their middle age, then their steady fusion stage, lasts a long time, relatively short, death, swelling, cooling, but as it shrinks it gets less bright, so it's actually going down on the size scale, but it's actually going to get hotter because it's condensing all that energy into a smaller space. Okay, just pick up on another crucial few little bits. This basically links in with spectrum, so we're going to do. So I'm going to put spectrum on. So basically around about 5,000 degrees you tend to get things glowing orange. If you're up around about this level, as you can tell from the pictures, yellow, we tend to be getting white hot around about 15,000 Kelvin, and then fairly obviously at this end we get blue hot, so it's beyond white, it's more of the blue ultraviolet end of the spectrum. Okay, so high temperature, I'll just put low temperature there. A few other things, you may have heard a few phrases. So this typically, some around here, is Betelgeuse, or Beetlejuice if you happen to watch the 80s film. We have things like Proxima Centauri, that's our closest star. That's close, but actually a lot cooler. Proxima Centauri, and two words there. So it's close to us. And then other ones that you can pick out, they occasionally get there, but basically the whole idea is this is a way of just mapping all that we can see, but realising that other stars flow through this process. So protostars, if they're big enough, will actually perhaps work along this main thing here, main sequence, and then they turn into blue giants, possibly into red supergiants, and then across the blue, and then So there's different pathways through this. You can spend a long time looking at this, but the basic idea is it shows that all stars go through changes, and the reason we know that is because we can see the process happening with all these different types of stars, and you can see where they're going from that. So by measuring temperature, by measuring luminosity, we can tell a lot about what the processes are inside the stars. And so really, astrophysics is basing everything on the physics of work you can do in the lab by looking at radiation. So that takes us into our next section.